Welcome back to the next video in our series of Let's Calc videos, where we go through the problems or particular questions from the problem sets each night in AP Calculus AB. In this video, we're going to focus on the basic differentiation, or if I could go back and rename it, the differentiation basics lesson and problem set. I'm going to talk about some problems that have some little twists to it, show you a little bit of everything, and go through the free response style of questions that are at the end, as well as make sure you've represented functions with tables, numerically, graphs, graphically, and of course algebraically. So we'll also talk a lot about notation and the different ways that we can be clued into needing a derivative. Without further ado, let's jump into the first problem. Okay, our first set of questions ask you to simply compute the derivative of each function. In other words, we're going to differentiate each function. Then they want us to name each result appropriately, meaning we want to use an appropriate notation to describe the derivative of this function. The first problem we're looking at here is question number 2. It gives us f of x equals 11 square root of x minus 10 over x squared. So now there are a couple different ways to approach this, and again, on your first day, you're going to probably be moving a little slower. Even you should be moving a little slower than you will in a week or two when you approach this. But a good starting point is to try to get this function, or any function you're attacking, into a polynomial power-based form that you can attack using the simple derivative rules we know. So for instance, in this one, I'm going to first write this as 11 times x to the 1/2 power, since that's the same thing as square root. And second, I'm going to write this as negative 10 times x to the negative second. What we want to do is we want to take that function, sorry, it's not f prime, that was f anyway. We want to take that function and we want to differentiate it. So that would actually be what's equal to f prime of x. So we want to take the derivative, that's what the d dx means, is we're going to differentiate this function with respect to x, and we want to see what comes out. Well, using the derivative properties themselves, first I see that we have a scalar in both of these situations. I also see that we're subtracting the 2, which I can apply two derivative properties right off the bat. 11 times the derivative with respect to x of x to the 1/2 minus 10 times the derivative with respect to x of x to the negative 2. Now again, you don't need to show this step. The properties are going to become implicit as you do your work, but it's a good starting spot. Now with that in mind, we can differentiate because we have x to a power and we have x to a power. So recall that the power rule states that the derivative with respect to x of x to the n power is equal to n times x to the n minus 1, so long as n does not equal 0. So at that point, that's when we have other issues to deal with. So in looking at each of these, first one will have 11 times the derivative, which is going to be 1/2 x to the negative 1/2 power. On this one, we'll have minus 10 times, bring down the power, x to the power minus 1, which will be negative 3. So truthfully, this is an acceptable final answer. It just looks kind of clunky. So to clean it up a little bit better, I'm going to do two things. First, I'll combine these into a single scalar. And this will become plus 20, x to the negative third. And then finally, I'm going to take advantage of those negative exponents. And I'm going to write them in a slightly different way. X to the negative 1/2 is the same thing as 1 over x to the negative 1/2, or 1 over x to the 1/2. So that's 1 over x to the 1/2. And I'll also point out, of course, that that's the same thing as 1 over square root of x. So this first term can be 11 over 2 square root of x. The second one can be positive 20 over x cubed. And there's definitely no need to find the common denominator. That's way more work than we were planning to do. That would be a final acceptable answer. So the only thing that I could add into here to really give you much more is to point out that you could also memorize, like we talked about this probably a little bit in class, but you could memorize the derivative rule for square root of x. Instead of thinking of it as x to the 1/2 power and ending up with this expression that we see on that side, we could instead just remember that it becomes 1/2 or 1 over 2 square root of x. Like that's one of those rules that comes up a lot, so it might be worth putting into your brain. Either way, there's our first problem. We broke things down. We used the derivative properties, maybe not showing as much work as I did. I tend to show a little bit more. And then finally, we differentiated using the power rule. Okay, next that takes us to question number 4. Question number 4 is not so simple as just straight up doing the power rule, because there's an issue that comes up in the form of the question. Our function is 4x to the 4th minus 2x cubed plus 3, all divided by x cubed. And as of this day, we don't have a rule for how to differentiate a quotient of two functions, or what do you do when you have a rational expression like that. So instead, we can't approach it using anything yet until we learn the quotient rule and its accompanying song. Yes, you will get to sing a song eventually. Instead, what we can do is we can look at this as a situation that begs for us to simplify the expression, or to at least aesthetically change the way it looks. So what I'm going to point out here is that if you have 5 plus 10 plus 15 over 5, that is completely equivalent to distributing that 5 in the denominator into a denominator for each fraction. And I think that's probably saying it in the most complicated way. What I'll point out is this is the same thing as 1/5 of 5 plus 10 plus 15. So in a sense, we can distribute the 1/5 in, and we'll end up with the expression you see up there. The reason this is helpful to us now is that we can rewrite y. In fact, sorry, funny sound. I just want to put that equal sign elsewhere. What we can do is we can rewrite y as 3 individual terms. We'll have 4x cubed over x cubed, or 4x to the 4th over x cubed, minus 2x cubed over x cubed, and then plus 3 over x cubed. So in a sense, what we're doing is we're putting it in position to eliminate the issue of the division and the quotient that we had to handle before. So taking this one step further, if we simplify each one, we get 4x minus 2 plus 3x to the negative third power. This is what we're going to differentiate now. So we're going to take the derivative with respect to x of this entire equation. Of course, on the left, we'll get dy dx. There are a couple ways to write this. So we could get dy dx because it's the derivative of y with respect to x. You might also see it written as y prime. Both are acceptable here. As far as the derivative itself, 4x is a linear function, so the slope would be its derivative. So we can write that as 4. The derivative of a constant, we said before, is 0. So we could just say plus 0 because it's a constant. And then the next one, we can use the scalar property, and we'll have the scalar of 3 times bring down the power, x to the power minus 1. And there stands our derivative. All we need is to clean it up a little bit. We'll have 4, it looks like minus 9 over x to the 4th. And there is our y prime, or dy dx. So again, in this case, the most important thing was that you could algebraically manipulate or massage the function a little bit to change its form into one that was better and more ready for us to differentiate based on the tools that we have so far. Next, that brings us to the function k of x. Now, k of x in itself has two simple polynomial expressions, so they'll be easy for us to differentiate. But the difficulty here is, of course, we're looking at a piecewise function. So the question in your mind might become, how do you take the derivative of a piecewise function? Like, was there any special trick that happens here? And there is a small little trick for us to adjust, but for the most part, it's as simple as just differentiating each part of the function. So for instance, what you can think about is we can imagine what the derivative is first of 10x minus 3, and then we can also think about what the derivative is of x cubed plus 7x. So evaluating each of those derivatives, the derivative of the first one is equal to 10, because that is just a line, so its derivative is its slope. By the way, if you don't trust that, you could also look at this as 10 times 1x to the 0, which would also give you 10, but your call. On this other one, we've got x to the third, so bring down the power, x to the power minus 1. And then we have another linear one, and that slope of 7x is just 7. So with that in mind, we found the derivative of each branch of the function, the top one and the bottom one. So to write out the derivative of the piecewise function, all we do is set up another piecewise function. We'll have 10 for the derivative for some values, and we'll have 3x squared plus 7 for some other x values. Now this is the one spot where you've got to be careful. No, our boundary is not going to change. We're of course going to be comparing it relative to 1. What changes is we can't guarantee that or equal to sign because of an issue called differentiability. It may be that when we take the derivatives don't match up right. Or if this function was discontinuous, the derivative couldn't possibly exist there. So to be safe, the one adjustment we make, and I'll even make it in a bright red color here, is instead of being less than or equal to, we'll just go less than, and well, the other one was greater than, so it stays greater than. So with nothing else said, there is our derivative. So the moral of the story is for piecewise functions, differentiate each branch, and then especially for now, careful with the less than or equal to or greater than or equal to. So odds are they won't be there, but there is our derivative now. So we found it. Okay, next, let's take a look at 8. 8 is in the same general world. It's asking us about differentiating. Here, though, it's not just asking us for f prime of x. It's asking us for f prime of 2. So we want the slope at a particular point. But also problematic here in question 8 is the presence of a product of two functions. And again, we don't have a derivative rule for a product of two functions, and that rule might not be what you think it is. There is in fact something special called the product rule that we're going to address later on in the course, a couple of days in fact. So in here, what we need to do is we need to first figure out a way to approach this function. What I'm going to recommend is, again, like we did with problem number 4, we just algebraically change the form that the function takes. So instead of x squared plus 5 times 2x minus 3, I'm instead going to multiply out those functions and figure out another way to do it. So there's lots of different ways to multiply. Some people might like the little double sprinkler or broken sprinkler strategy. I'm going to choose polynomial multiplication with a method that I was taught a long time ago, or I was taught when I first began teaching. So we have x squared plus 5. I'm leaving space for the 0x term that's in there, just in case. And then we have 2x, minus 3. And we're going to multiply these guys. So starting out, we'll go 2x times x squared is 2x cubed. 2x times 5 is going to be 10x. And in fact, I'm just playing it safe here. I'm going to move this out a little bit further. Since again, what you can kind of see is I'm trying to match up the degrees as I go through. So, sue me. Next, we just did 2x. Next, we're going to look at negative 3. So negative 3 times x squared is going to be negative 3x squared. Negative 3 times positive 5 is going to be negative 15. Combining all our pieces together, we're going to get that f of x, while still equal to that product, is equal to 2x cubed minus 3x squared plus 10x minus 15. So what we've done is we've transformed the function significantly. No longer are we staring at that awkward product. Now we've just got a traditional polynomial. And if we go to do the derivative of this guy, we can use all our properties from before. So I see a bunch of scalar and powers. So first we'll have 2 times 3x squared, because the derivative of x cubed is bring down the 3, x to the 3 minus 1. Then we'll have minus 3 times 2x to the first. For the next one, we have a linear expression, 10x, so the derivative is 10, or 10 times 1x to the 0. And the derivative of negative 15 is 0. So simplifying things here, we get 6x squared minus 6x plus 10. And that is f prime of x, but don't go patting yourself on the back just yet, because we want f prime of 2. So if that's f prime of x, f prime of 2 is going to be equal to 6 times 2 squared minus 6 times 2, all plus 10. That's going to be equal to 24 minus 12 plus 10. That's equal to 12 plus 10, which is 22. And there is our derivative that we were looking for. So in this case, again, algebraically maneuver the function into a form that we can differentiate without needing any advanced rules. And then, of course, at the end, plug in x equals 2. So either way, we get our derivative of 22. Okay, that brings us to the second set of questions on the problem, or the second focus, which is, of course, writing the equation of a tangent line, one of the ultimate questions of calculus as it was being developed. It does say in here that we're supposed to use the derivative, of course. We're going to leave each tangent line equation in point-slope form, but otherwise we're going to approach everything there. So a couple things before we jump into tangent lines. First, if you'll recall, a tangent line equation should be written, just for simplicity, in point-slope form. And point-slope form requires 3 things from us. It requires an x value, it requires a y value, and it requires a slope. So the x value is typically given. You'll see that some of these questions it's not given, because I'm clever. This one, the y value, we sometimes are given, but sometimes we have to find. And then finally the slope we have to find and calculate, and that's going to be using the derivative, because the derivative produces a function that gives us the slope or instantaneous rate of change at any x value. So in looking over here, before we jump in and start thinking about the derivative for this point-slope form problem, I see h of x as negative 10 over x plus x over 4. I'm going to start, since we have x equals 2, by figuring out what is the y value. And the y value we're looking for is going to be h of 2. So plugging that in, we'll have negative 10 over 2 plus 2 over 4. This gives us, actually I'm going to leave that negative 10 over 2 for a second. That's negative 10 over 2 plus 1 over 2, which is negative 9 over 2. So what that gives us is our y1. So y1 is now found in our equation. And of course, x1 was given to us, so x1's found. All that's left is the slope. So with y found, or the y value found, we next want to calculate h prime of x. And as with the other situations, h prime of x is going to be the derivative with respect to x of negative 10 over x plus x over 4. And of course I've chosen this problem because that derivative is a little bit crunchier than the average one. So a couple things here. We want to transform this into a better form for us to differentiate, something that screams power rule and rules that we know. So first, if we have negative 10 over x, that's the same thing as negative 10x to the negative 1. It's one of the most common techniques for differentiating that you'll see here. Second, we have plus x over 4. I want to point out that x divided by 4 is the same thing as multiplying 1/4 by x. And the reason I write it in that form is that makes it a linear portion. At least that part of the function is linear, which means the derivative is just the slope. So with that in mind, we've now found our function form that's easy to differentiate. So let's do it. I'll use the scalar property first. So negative 10 times bring down the power, x to the power minus 1. And then for the linear function 1/4 x, the derivative is just 1/4, or 1/4 times 1 x to the 0. So with that in mind, we get that our derivative is equal to positive 10 x to the negative 2 plus 1/4, also known as 10 over x squared plus 1/4. And at this point, we want to calculate specifically the slope at x equals 2. So oftentimes you'll see in my work, I'll draw an evaluate line and then say x equals 2. You could also simply write h prime of 2 is equal to, and you'll have 10 over 2 squared plus 1 over 4. For simplicity, I'm not going to change anything here. This will be 10 over 4 plus 1 over 4, which gives us 11 over 4. So that is going to fill the role of our slope. So with that slope calculated, which again is a number, it's got to be a number. It cannot be a function of x. This has to be our slope. We can then write what the tangent line is equal to, or what the tangent line equation happens to be for this particular function at this particular point. So the tangent line is going to be y minus a negative 9/2. So I'm going to make that a positive 9/2. And that's equal to the slope, 11 over 4, times quantity x minus 2. And that gives us our tangent line equation to the function we were looking at. So pretty straightforward. Important stuff is calculating out your y value, differentiating properly, and finding your slope. And then, of course, constructing it that way. And as a reminder, one more time, you do not need to multiply it out. We want it to be in point-slope form. It minimizes the arithmetic you have to do, which both saves you time and saves you the possibility of making a mistake. So there is number 12. Okay, next let's take a look at 13. 13 is another find the tangent line equation. In this case, though, there's something very different. Obviously, you might be like a little bit weary by seeing that cube root of x in the denominator, but that's actually not going to be too bad. Instead, what I want to point out is that we are given the task of finding the tangent line when y equals 3. So they did not give us an x value this time, they gave us y. So in this case, everything's kind of backwards. We're aiming for y minus y1 equals m quantity x minus x1. And in this case, we don't know x, we're given y1, so we need to find x1, x sub 1, and we need to find the slope. So in here, let's start there. It's a little bit more of a challenge, but let's take a look. So if y equals 3, that means 3 over the cube root of x plus 4 has to equal 3. Now doing a little bit of algebra, we can subtract 4 from both sides. That would give us that negative 1 is equal to 3 over the cube root of x. And from there, we've got a little bit of work to do here. So I'm going to do two things at this point. If that's true, then it means the negative cube root of x has to be equal to 3. And that's the same thing as saying the cube root of x has to be equal to negative 3. From there, I'm going to cube both sides. Look at all this algebra it takes to get there. After all that, we get that x is equal to negative 27. So there's a huge amount of work to get the x value, but now that we have it, everything else should unravel pretty nicely. We have x, we have y, we're just looking for the slope like normal. We just had to do it a little bit backwards. So from here, to find the slope, we want to calculate y prime. That's once again going to be the derivative with respect to x of the function we have there. In here, the plus 4 obviously is plus 4, but I'm going to rewrite that first term as 3x to the negative 1/3. So the 1/3 power is because of the cube root. The negative is because it was in the denominator when it began. So from there, this puts us in position to do a really nice, quick little derivative rules with the power and scalar rules. So this will be 3 times bring down the power, x to the power minus 1. And then, of course, the derivative of 4 is 0. So that comes out pretty clean. So simplifying a little bit, we get negative 1 x to the negative 4/3. By the way, that's because the minus 1 is 3 over 3. And so this is the same thing as negative 1 over x to the 4/3 power, which is lovely, but not so simple in itself, because now we need to evaluate this at x equals negative 27. So in looking, y prime is going to be equal to negative 1 over negative 27 to the 4/3 power. And in simplifying this, which again you might be a little bit rusty on, there's 2 ways to approach it. I'm going to go this way. 4/3 power, like let's go this way. X to the, yeah, that's fine. X to the 4/3 power is the same thing as the cube root of x to the 4th power. So I'm going to write it that same way. This will be the cube root of x to the 4th power. Or sorry, the cube root of, not x, negative 27. Well, we already talked about the cube root of negative 27 earlier. That means this is negative 1 over negative 3 to the 4th power, which has a slope then of negative 1 over 81. So that is going to be our m in this case. So we've now found m, and that means our tangent line is going to be y minus 3 equals negative 1 over 81. That's ugly looking slope. No. Negative 1 over 81, x minus a negative 27. Yeah, geez. I was ready to box that perfectly and be happy, and failed. So there is another tangent line at play. Hopefully that clarifies that a little bit and gets you comfortable again with some of those little exponent rules and things like that that we've addressed before. Alrighty. So the next question we're going to hit is question 15. Question 15 involves a little bit of problem solving and is again one of those like tangent line questions where things are asked in kind of a roundabout way. You're told at the beginning that y equals 22x squared minus 6x plus 3. So a pretty simple function to differentiate if it comes to that. And it says at the point xy where dy dx equals 22, what is the equation of the tangent line? So this one's weird. We've had problems where we're given x to start. We've had problems where we're given both x and y. And we've had problems where we're given y. In 15, we are given the derivative and nothing else. So if dy dx is equal to 22, where we need to begin is we need to figure out what dy dx is, and then solve for the x or y value that will make this equal 22. So let's start right there. If y is 2x squared minus 6x plus 3, then y prime is going to be 2 times 2x minus 6 plus 0, which is equal to 4x minus 6. So interestingly enough, our derivative is with respect to x and is in terms of x. But what we were told was that dy dx is equal to 22. And since y prime is just another notation for dy dx, and that's equal to 4x minus 6, we know that this has to be equal to 22. And if 4x minus 6 is 22, that means 4x equals 28, and that means x equals 7. So already, just by taking the derivative and setting it equal to 22 using the info we were provided, we know now that x equals 7. And of course, if x equals 7, in order to find y, we can find y of 7 by simply plugging 7 into the function. So instead of 2x squared minus 6x plus 3, that's 2 times 7 squared minus 6 times 7 plus 3. That's going to be 2 times 49 minus 42 plus 3. That's going to be 98 minus 42 plus 3. That's going to be 56 plus 3. Let me make sure that works. 56, yep, plus 3, which is 59. So right there, we just found that y has to be equal to 59. And given that we were asked for the equation of the tangent line, we now have all the ingredients. We have that the tangent line must be y minus y1 equals mx minus x1. And there is the tangent line. And again, we didn't even know the point, we just knew what the slope was. But since our function was quadratic, there was only one x value where the slope could possibly be 22, which allowed us to answer this question pretty quickly and smoothly. Okay, next, that brings us to question 17. 17 asks us, this section asks us to evaluate each limit using the definition of the derivative and our new differentiation rules. So basically there's two parts here. It says using the definition of the derivative, but basically I'm going to let you know right now that that portion isn't any sort of evaluation. This is just to recognize the function. So basically what you're going to be given is you're going to be given the limit of the difference quotient. Your job is to read that limit of the difference quotient and figure out what the function is, as well as what the x value might be. And then once you know what the function is, use our new differentiation rules to find that derivative. So basically we'll use the skills that we've developed today. So for instance, let's take a look at the problem over on the left side. So this one that we're trying to evaluate, which is number 17 right now, is the limit as x goes to 2 of the cube root of x minus the cube root of 2, not a great number, irrational for sure, all over x minus 2. So before I jump in, I try to start by recognizing the derivative definition identity we're looking at here. Since I see x minus 2 and an x approaching 2 in the limit, that tells me that what we're looking at is the limit as x goes to c of f of x minus f of c all over x minus c, which we know is equal to f prime of c. So the reason that we start here is that this gives us an opportunity to recognize what f of x is. As I said, that's the goal, is to figure out what the function is. So in looking, f of x occurs right there. So in this case, I'm seeing that f of x must be equal to the cube root of x. And then second, the c value is what appears down there. And in both cases, I see x equals 2. So we're interested in the value of the slope of cube root of x at x equals 2. Huge starting spot for us. Now that we have it, our job is to actually find it. So what we need is f prime of x. In order to find f prime of x, we're going to take the derivative with respect to x of the cube root function. But the cube root function is the same thing as x to the 1/3 power. And using our derivative rule for x to a power, we can bring down the power, then multiply times x to the power minus 1. That's going to be 1/3 x to the negative 2/3, which is the same thing as 1 over 3 x to the 2/3 power. So there's our derivative. We specifically want, though, not f prime of x, but f prime of c. And there's our c, x equals 2. So what we're calculating here is f prime of 2. In fact, you could even say at the beginning, this is equal to f prime of 2. That's going to be then equal to 1 over 3, quantity 2 to the 2/3 power. And truthfully, I might be tempted to just leave that as my answer, because it's not going to simplify very far. But for the moment, something that we could do, should have made this 8, geez, oh well. So in this case, what we can do, the only simplifying that we could go with, if you don't want to settle for that as your answer, because it just looks a little clunky, is you can take advantage of the fact that 2 to the 2/3 power is the same thing as the cube root of 2 to the 2nd, which means this is really 3 cube root of 4. So this might be the preferable version of that slope if you so desire, but easy to evaluate either way. Okay, and the last problem I'm going to do before I pause for the night to go do an escape room with a bunch of teachers from the math department is I'm going to do question number 19. It's the same section, so the same instructions. We're supposed to use the definition of the derivative and our new differentiation rules to evaluate some challenging limits of difference quotients. So in looking up here, I see that h in the denominator, which already tells me right now that we're looking at the traditional derivative definition, which is the limit as h goes to 0 of f of x plus h minus f of x all over h. So that's where we start. And then as I look inside this thing, that h was important, but I noticed that there's no number that's been evaluated in here. That tells me that the expression we're looking for isn't f prime of 4 or something like that, f prime of c of any kind. This is literally equal to f prime of x. So what we literally want is the derivative of whatever function it is that we're evaluating there. So as we've done recently, including like on the previous problem, I think, f of x is right there at the end. So our function that we're interested in is this guy. I call it this puppy, but again, some people are allergic. So sine of x minus x cubed appears to be our function. And that's f of x. All we want is f prime of x. So we're just going to take the derivative with respect to x of this expression. That looks like a sum problem and a power rule, or sum indifference rule and a power rule. Taking the derivative of sine, you should just have that in your head, or get it used to getting in your head, as cosine of x. And then for x cubed, it's minus 3x squared. So there is the result we were looking for. And by the way, you might notice that I didn't write f prime of x down here and box that. It's because there was no actual f of x in our problem. That was just the notation that I use in the traditional definition of the derivative, and it's just a way to kind of help explain what it is that we're looking at here. So in a sense, you don't need that f prime of x. It's technically wrong because there's no f in here. I'm probably not going to lose you a point, but just something to keep an eye on. But definitely the derivative is cosine of x minus 3x squared. Alrighty, so let's take a look at the next question. The question is going to be number 21. This is the only true or false statement on the entire page. And the statement we're supposed to determine whether or not it's true or false and explain our reasoning for is if f prime of x equals g prime of x, then f of x equals g of x. So in a sense, what we're saying, or what we're trying to figure out, is does the equivalence of derivatives, and using an equal sign probably isn't the best option there, let's fix that. Do equal derivatives imply we have the same function? And in this case, as we start to think about that, another way to do it is to transform it into a question. So in other words, we could seek out counterexamples. Are there two different functions that have the same derivative? And the answer here might not at first seem like the answer is going to be that there are such functions, but keep in mind this. If you take the derivative of any constant, you get 0. So what that tells me is, if you add different constants to a function, to whatever function you so choose, then you'll end up with the same derivatives, but have different functions. So in looking here, I'm going to do exactly that. I'm going to find a counterexample. So f of x, let's let f of x equal x squared, and let's let we already did f of x. Let's let g of x equal x squared plus 11. So with that in mind, if we look at those two, let's think about what f prime of x is. Well, f prime of x for x squared is 2x. It's one of the first derivative rules we find. I think we even used it to derive the rest of the differentiation rules, or for x squared. And the derivative of x squared plus 11 is 2x plus 0, which is 2x also. So what we found was a situation where f prime of x equals g prime of x, because both of these guys have 2x as their derivative, but f of x does not equal g of x. And what that means is we've just found our counterexample, and that means our statement is false. So an important thing to remember, it's actually going to be huge when we get to the second term, or the second half of calculus, and start talking about anti-differentiation. But for now, just a nice way to check and see if you understand how function derivatives don't actually do it. It's also worth pointing out that thinking about the fact that you can have equal derivatives but different functions means differentiation actually loses information. It loses some specificity from what the original function would have had, which is kind of an interesting thing, but there we go. So that was the true or false statement, question 21. Okay, next this brings us to question 22, which is a multi-part. I think it has 3 parts to it. On 22, you're given a table of values, really common way to deliver information about a function. In this table of values, though, for the first time, we have information about the function f of x, and we also have information about the function's derivative f prime of x. So we actually know a ton of information from the slope. And we're supposed to use that information to determine the equation of the tangent line. Or to, answer some questions, including some about tangent lines. So in question A, this one isn't actually particularly difficult. This is actually focused on just getting you comfortable reading the table. So they want the equation of the tangent line to f of x at x equals -2. So our typical tangent line is y minus y1 equal to mx minus x1. Based on the information that's here, we basically want y minus f of -2 equal to f prime of -2, since that's what slope is, right? The derivative at the specific point, times x minus a -2. So what we need to calculate is f of -2 and f prime of -2. Well, look at our table. X equals -2 corresponds to an f value of 3, which means f of -2 equals 3. so this side will be y minus 3. F prime of negative 2 is going to be the slope right down here, which is negative 5. And voila, without having to do any real arithmetic, we have our tangent line. So again, for 22A, the job was just to get you comfortable with reading the table and reading out the information that you need. Nothing particularly difficult, nothing really advanced here, just constructing a tangent line and reading a table. Okay, part B, 22B. This one starts to contribute a little more work. This one starts to use some of the derivative properties and to start to look at things a little differently. For part B, it says let h of x equal 4 f of x plus 3x. So we've got some sort of function transformation here. We are told to then compute h prime of 4. So now be careful. Don't fall into the trap of just saying negative 7. Because while negative 7 has something to do with our answer here, that is f prime of 4, not h prime of 4. So before we can get anywhere else, if h of x is equal to 4 f of x plus 3x, we need to differentiate this equation in terms of x, or with respect to x. Oops. So we need to take the derivative of both sides. Well, the left side, we already have a notation for that. It's going to be h prime of x. On the right side, we have derivatives that we need to take. So looking at this piece, the first one is we have the derivative of 4 f of x. It's going to be the same thing as 4 times the derivative with respect to x of f of x. And again, I'm being super slow here. Obviously, you go a little faster. Then we need to take the derivative with respect to x of 3x. Well, evaluating these pieces, we have 4 times the derivative of f. We call that f prime of x. And the derivative of 3x is just a line's derivative, which is just a slope, which in this case is 3. So there's our derivative. That is h prime of x. But remember, we weren't asked for the derivative h prime of x. We were asked for h prime of 4, specifically the slope at the x coordinate, x equals 4. So in here, that means, this point means we need to plug in x equals 4. And again, we can't leave that as our answer because it has an unevaluated function. We are responsible for pulling that information out of the table. Looking at our stuff here, obviously the 4 and the 3 aren't hard because they're not from the table. F prime of 4, we have f prime, or we have x equals 4 and f prime. The value we're looking for is right there at negative 7. So see, we did need it. That means we get negative 28 plus 3, which is negative 25. So works out pretty nicely. There's the derivative we were looking for. Again, reading the table, but also taking advantage of some of those derivative properties. In particular, we use the scalar property, and we use the sum and difference property. Maybe even the linear property if we decided to define one of those. So there it is, 22b. Okay, that brings us to 22c, the final question from this portion, from the extended question 22. This one's set up similar to 22b. It says let k of x equal 2/3 f of x minus 5 root x. Find the tangent line to k of x at x equals 1. So we want the tangent line once again. We're again going to be using the table because the function we have k is dependent on f of x. So we're going to have to evaluate and differentiate this function and then use the table to fill in the missing pieces. So looking here, the first thing I'm going to do is I know that in our tangent line equations, we are always looking for the ingredients we don't have. Well, we know x1 is 1 because they told us. We need the slope and we need the y value. So to start things off, I'm going to go with the simpler y value. So I want to calculate out what k of 1 is equal to, and that means we're going to plug in 1 for all the x values. So we'll have 2/3 f of 1 minus 5 square root of 1. Looking at our table then, that's going to be 2/3 f of 1, which appears to be 8, minus 5. And then if we simplify stuff, we have 16 over 3 minus 15 over 3, because of course we can multiply up and down by that. And we get 1/3 is our y value. So that gives us y1. Now we just need to find the slope. So for this piece, we need to figure out first what k prime of x is, so that we can have a function that delivers us the slope. Looking at our equation up there, go through, we're going to differentiate this guy. Oh, I don't want to box it. We're going to differentiate that. So looking at the derivatives, first I'm going to use the scalar property. I'm not going to write it out in the same depth I did on the previous one. Bear with me. So scalar property says 2/3, and then the derivative of f is f prime. Next we have 5 times the square root of x. Well, we've said before that the square root of x is 1, or x to the 1/2 power. So you can either go off to the side, and remember that x to the 1/2 is 1/2 x to the negative 1/2. You could write that as 1 over 2x to the 1/2. Or you could go with the notation that I recommend that you just commit to memory, which is 1 over 2 root x. So this becomes minus 5 times 1 over 2 root x. Simplifying just a little bit for clarity's sake, we get this. And now we want to evaluate that at x equals 1. So we want to plug it in. So k prime of 1 is going to be 2/3 f prime of 1 minus 5 over 2 square root of 1. Again, looking at our table, f prime of 1 is 6. So it's going to be 2/3 of 6 minus 5 over 2. That gets us 12 over 3 minus 5 over 2. It's become an arithmetic problem. We have 4 minus 5 over 2. It's the same as 8 over 2 minus 5 over 2, which is 3 over 2. So that just gave us the slope that we were looking for, and after all that, we can finally put in our tangent line. It's going to be y minus the y value, which I believe was 1/3, equals the slope 3/2, x minus the x value of 1. So there is our tangent line. Again, not particularly difficult, but nonetheless, definitely using some of these properties. It might feel a little bit weird the first couple times you do this and you differentiate what we might call an abstract function. But again, all the information we need is in that table. These are efficiently written, and hopefully that's helped guide you through the process with your first one. Okay, the last questions of the assignment, the problem set for this one, focus on a graphical function and a graphical interpretation here for us to look at. In this case, they give us a graph of some function g of x, and it says the tangent line to g at x equals 2 is shown. So that means that this guy is the tangent line that we're interested in. So interesting kind of question, maybe not as calculus-y as you might expect. And look at that, in question A, we want the equation of the tangent line to g at x equals 2. So basically we need to figure out what is the equation of this line. Now don't panic, because that equation is not going to be hard to find. First and foremost, seems to be a missing dot right there. First and foremost, oh, it didn't show up on the picture either, I'll have to fix that. Fix the assignment, right there, close enough. Okay, so in writing the equation of this tangent line, we just need to figure out the equation of the line. Well, a couple things here. First, if we want the equation of a line, typically we think of y minus y1 equals m x minus x1. But the difficulty here is we don't have any real context at the beginning for what that y value is right there. So instead, I'm going to remind you that this is the same as y equals mx plus b. And the reason I want to go in that direction is because the two ingredients there, m is our slope, and b is our y-intercept. And both of those two things are very clear and easy to read off the problem. Specifically, m is going to be the slope. Well, looking down here, we go down, oh shoot, sorry, not right there. We go down 7 and over 5, which tells me that my slope is negative 7/5. And for the y-intercept, it's labeled for us. We literally know the y-intercept is 7. So in other words, right up there, it hits at 7. So b equals 7. And without having to do any point slope form work or anything even really advanced, we can simply say that the tangent line equation is negative 7/5 x plus 7. Now, if we were asked to then find something like, say, g of 2 or something like that, we could use the tangent line to find it, but this question was actually very forgiving and generous and only asked you to find that far. Okay, that finally brings us to the final question on the assignment, 23b. It says, let d of x equal k times f of x plus 1/5 x squared plus 3 for a real number k. Then it says, if d prime of 2 is 1/2, find k. So this is one of those search for the missing value questions. So let's dig right in and go. So we're told information about d prime of 2. So of course, given d, we need to find d prime of x. Now since k is a real number, that means that this k in front is simply a scalar. So in other words, we can treat it just like if it was a 42 in front, maybe with less reverence because it's not necessarily 42, but whatever. So in other words, the derivative of k times f of x is going to be k times f prime of x. Again, because it's a constant, it's a number, it's a scalar. For the next one, we're going to have 1/5 times the derivative of x squared, which is 2x, and then plus the derivative of 3, which is 0. So for our purposes, d prime of x is going to be k f prime of x plus 2/5 x. And so that is the derivative of that new function we created, d of x. For our purposes though, remember we don't know what d prime of x is or anything, we know specifically d prime of 2. So if we add these ingredients together, d prime of 2 is going to be k times f prime of 2 plus 2/5 times 2. So in other words, we're evaluating this function or this expression at 2, or we're plugging in x equals 2. And then, of course, not evaluate. We know that d prime of 2 is equal to 1/2. So we need to solve this equation for k. And I think we can do that. So reading up on our picture, they want f prime of 2. Well, f prime of 2 is just the slope of this line. And everywhere we have that, the slope is -7/5. So in fact, we've got that ingredient already. Over here we have plus 4/5, and all of it's equal to 1/2. So now in here, I'm going to do a couple things. First, hopefully you'll forgive me for a second. I'm going to rewrite this just for clarity as -7/5. Also have to go somewhere pretty soon, so I'm trying to speed up. So from there, I'm going to start there. I want to solve for k, so there's a couple things to do. What I'm going to do first is I'm going to multiply both sides by 10. And since I don't have to do this, I'm just choosing the fraction bus for simplicity. So I'm going to distribute that into each of the pieces. So that'll end up giving me, let's see, that's going to be -14k plus 8 equals 5. I think I did that right. We'll find out. Probably is okay. Then from here, I want to solve for k. So I'm going to do two things. I'm going to subtract 5 from both sides and add 14k. Is 14 carat? It reminds me of diamonds or something. Go figure. So this is going to be 3 equals 14k. And with that in mind, that means that k should be equal to 3/14. And now we could, if we desired, we could go through and actually check to make sure that this answer did work. And since I was doing this pretty fast, I'm going to check it, even though that makes it take longer for me to leave. So in here, looking at our ingredients, if we have k, I'm going to take this equation basically. So if we have k as 3/14 times f prime of 2 is going to be times -7/5. Then we have plus 2/5 times 2. And we want to see if that does equal 1/2. Let's see. That's going to be simplifying pieces. We'll have 2. This is going to be 3/10. Did I do that right? Oh, sorry, -3/10 because that negative sign up there. -3/10. This is 4/5. That's the same thing as -3/10 plus 8/10, which is equal to 5/10, which is 1/2. So this does in fact check. We found our correct value. And without further ado, that ends the problem set video solutions. Hopefully this has been informative and helpful to you. Thank you for watching, and hopefully you'll be able to differentiate between all the different techniques you've learned today and learn to use fast.